So full disclosure, if you need to go get coffee because you want technical content, and this is not technical content. I want to be really clear. Like I'm about 6 light years behind Brooklyn there. But I wanted to take a few minutes to talk about how we look at compute over data in the world, and in particular what the landscape looks like as we see it. And by we, I mean, for those that don't know, the Bacalhau Project first started, in February of last year, thanks to the, foresight of Protocol Labs that we got this underway to enrich the Filecoin ecosystem generally. But really, we started to see real commonalities across all of distributed compute, whether or not it was Web 2 or Web 3, existing compute networks, new compute networks that were coming online. And so what I'd like to talk about today is what we see as the reasons for success for many of these distributed compute networks, these decentralized compute networks, why they came about in the first place, and in particular, where we see success for folks who are implementing them and avenues to explore. So the landscape that got us started here is what you see in front of you. There are kind of, I like to say there are 3 immutable facts in the world, right? One is, or there are many immutable facts, we just chose these 3. The first is that data is growing rapidly, right? This is not dispute. 42% year over year, 60% of companies today manage more than 1 petabyte. Most of it, or entirely, is on-prem, detached from any kind of decentralized network or anything like that. Though, interestingly, according to Gartner, 57% of it is outside of your traditional data center. So while we think of, somebody just has a massive set of S3 buckets or something like that, that's actually not the case. More than half of their data is sitting distributed, on-prem, on edge, on device, whatever it might be. Which leads to set number 2. Moving that data is slow and expensive, right? This stat we found was really fascinating. Data growth has outpaced network growth by 45% every year since 2010. So every year the problem is getting worse. You're getting more and more data, on nearly 50% more data than you have network capacity to support it. And the sizes, the 175 zettabytes projected by 2025, is so enormous it would take 1.8 billion years if you decided to move it over, standard networks. But even if those 2 weren't a problem, you would still have a need for distributed and decentralized networks because approximately 100% of it is under some form of governance. Could be GDPR, HIPAA, SOX, you name it. Any enterprise who is engaging with data today has some overseer who's saying, hey, you know what? You have someone's address in here. Are you treating that properly? And most of the time they're not. $250 billion in fines since 2008. So a lot of problems, a lot of headaches. There is absolutely a need for a new paradigm because 68% of all enterprise data is unused. Okay? So that is big data. How are people kind of addressing this today, right? They have a lot of problems sitting in front of them. Well, what we've seen when we looked at everyone is basically one of these 3 things. One, they look at using centralized systems that are usually provided by some external service. Or 2, they're like, you know what, we know our requirements better than, all those distributed systems experts out there. We're going to build our own system. Or they do nothing. And I'll get to what that is in a second. So let's start. Using a centralized system. When I say centralized system, I mean one of these very, very successful centralized systems today. Some that are more focused on compute, some that are focused on data, some that are focused on higher level constructs like how to do distributed training, ring reduce, things like that are very ML specific or other things like that. They're all, all of the things you see up here are used by literally millions of people. So they're very successful, but there's still a huge gap. And the gap looks something like this. So what you have is you have your central API server sitting up there. And then they sit over the top of a set of compute nodes, and those compute nodes sit over the top of a set of data. And you have your data scientist come along, and she says, well, I'd like to run some data analysis. She contacts her central API server. That goes through to the data. She gets her results back. All is successful in the world, right? This is all how it should work. This is the happy path. However, you usually don't get something as pretty as this, right? Usually you get your data spread all over the world, oftentimes much closer to where different isolated forms of compute are. Maybe your jobs are out there. Maybe you have particular needs because you need to be on device or on vehicle or whatever. Maybe you have free credits on AWS, whatever it might be. Your data isn't so convenient as to be located right next to your central API server. So now she says, well, I'd like to run this outside of my core data center. She contacts her central API server. Her central API server has no idea what to do. Or it attempts to do it, but now that it begins to cross these latency boundaries, that's where the problem starts. Because more often than not, those central API servers, they are designed to have a permanent connection with Heartbeat and other mechanisms to make sure that they know exactly what the jobs are, how they're running, and so on and so forth. That is critical, and that is something that everything you saw up there was not designed to handle. Most of those things were built in the late aughts, early 2010s. They attained massive success, but they were built at a time when data was much smaller and the network to data difference was much smaller. So then they run into this problem. Their central API servers aren't good enough. They're going to build a layer themselves. Now, that doesn't mean they're going to go and reinvent Hadoop or Kubernetes or something like that, but they often will build some form of muxer or other system that layers on top of it. But you're building on top of sand at that point because the systems still need to be able to handle these latency boundaries and basically reinvent distributed computing. So you ask your developer to go and do this. She says, I can build it. Great, go to it. She goes, she builds it. She has her custom orchestration system that sits on top. She says she'd like to go do that. And now the system is built and it goes off and runs. Right? We're done. Except she'd like to do one of these many new functionalities that are normally not provided by those central API servers. And the reason they're not provided is because those central distributed systems are more often than not very generic. They are expecting you to add this on top, but they're expecting you to add it in a way that is compatible with their centralized system that they have built. So if I tried to, look, I love Kubernetes to death. I used to run this stupid thing I used to run product management for it, but it does not like when a node disappears for even 30 seconds. It gets very mad at you. It kills the job, it kills the node, and assumes that when it rejoins, it is untrusted and blows everything away. That's 30 seconds. Now that is by default. You can make changes, you can have a different admission policy and things like that, but that's how it's built. And that is just admission. That is just disconnection, which happens all the time. Network partitioning happens even if you are like all inside of a single VPC on AWS, let alone you have a bunch of sensors sitting over there in the hotel trying to connect to your data center in US West, right? And these features are not particularly amazing features. They're pretty basic things, but people need them. And your poor developer is like, well, great, that's a lot of stuff. I want to go on vacation. My job, I didn't come here to go and rewrite orchestration systems. So she's gone, and now our data scientist is lost, right? So then what happens more often than not is people do nothing. And this is a real example. So here you have a bunch of cameras. Our police state is operating as functioned. We have many cameras out there collecting all this information about people in cities walking around. Great. Sounds good. We're going to reduce crime. We're going to reduce whatever, car theft, who knows. You would like to push all those to a central data center so you can run ML models, object detection, you name it. Except that is an enormous amount of data. In fact, in this city example, this real life city example, that's 4.4 petabytes a day. Do you think that data center is prepared to receive 4.4 petabytes a day? I think you know what the answer is. The answer is no. So what do? Instead, they have it go to local instances of that where workers are simply looking at the things, scanning it, and maybe, if you're lucky, retaining this for a short time. In this case, 7 days. And what happens after 7 days? Into the round file. So they don't even get to the central data center. There's not even the use of all these amazing models and object detection and so on and so forth because you're still having human beings do it. So this sounds terrible. Why are they doing it? Because it works. For better or worse, it works. It does something. Those people who were watching those videos saw some, bad behavior. They were able to collect some data, so on and so forth. So it mostly works, right? But it's better than what they have today, which is nothing. But it's worse than what we know we can get to. So our solution is to start, let's help these people by building open source compute over data platforms that work, right? So what would that look like? Well, again, and you're not hearing me talk about specific platforms right now. I'll get to that in a second. But let's talk about this and say, instead of using something that this person custom developed on their own, we're going to have them develop an OSS, using an OSS, compute over data platform. This is one where it leans into the fact that, like, hey, this is the reality of how systems and data and things are collected today. And this is how our system is resilient to these components of CAP theorem, right? The fact that things partition, the fact that availability can be intermittent. Having systems built for that changes a lot of this conversation. So now it's open source and extensible. It's built for multi-cloud. And it's also made for non-data centers. So, again, instead of expecting a full VM with all of Linux installed, you can run these on Edge. You can run these on Raspberry Pis. You can run these on, very locked down devices. Our developer still wants to go on vacation, and that's fine because it's maintainable, right? You have an open source community that you are participating with. And if you've chosen one, and again, more often than not, people will choose based on the quality of the community that supports it, you're going to have public maintenance or open consultants and things like that. So everyone's happy. And now, instead of having this, 4.4 petabits a day, let's do something with it. Instead of having workers look over this, let's instead replace those with a distributed set of machines, move that very high, high amount of bandwidth, high amount of video to those local machines nearby, thereby not overloading your central data center, do your object detection or other work at the edge, and then move back only the results. So you can say, oh, you know what, I had a model that looked at video, and it captured, any anomaly in there, and now I'm only going to move the 1 minute snippet back instead of all unnecessary raw data. So solution number one, or the first step towards this solution, is let's go and work towards open source compute over data solutions that work. But that's not we're at Filecoin. It'd be crazy for us to stop there. Let's go even further. The better solution, even beyond that, is to look towards decentralized open source compute over data platforms, but not platforms, protocols, right? So talking about how we treat this in a sophisticated way where these become protocols that anyone can go and implement and use, and you can plug into your higher level abstract of choice. So now we're going to use a decentralized protocol instead. Now you're able to communicate with the compute over data protocol. And what does the protocol actually look like? Well, in this case, you have your data scientist. Instead of her talking to a single open source API server, she's now talking to an open source protocol and any network that supports the concepts in there. So here, I've drawn this up. You have a universe of compute here. This could be end users. This could be new storage providers. This could be anyone in the world. They all have different types of data hosted on their platform. Our data scientist said, well, she'd like to run an analysis on dataset triangle. So she says, great. The nodes in the network that have that available volunteer. And they say, hey, you know what? I have that available. Now, all the rest of the nodes also volunteer just in case the nodes that have that don't have the compute available. But in this case, just the ones with triangle volunteer, so they all say, pick me. Then she adds additional layers on top. She says, you know what, I'd like to do this, but only in a HIPAA-compliant way. Who out there is HIPAA-compliant? They, 2 of them respond, and 2 say, well, that's not me, I'm going to drop out. Now, again, this doesn't mean that you're going to allow people to self-report a lot of these things. Oftentimes, you're going to have higher level constructs or reputation systems or things like that craft how to verify that this person is doing this, and these can all be built into your protocol. And then you say even further that I'd like to do this at the cheapest rate, and people volunteer the amount of that they're willing to pay as well, or the amount that it will cost to run on their particular systems. Someone says, it's me, and now she's able to choose exactly what she wanted, exactly her criteria, and deploy. And again, this is all protocol-based, right? Any network could communicate along this way and implement these things, and ideally, they will. Because decentralization is about maximizing choices. If I say, hey, you know what, I don't need to run in a HIPAA-compliant way, so therefore, I'm going to remove that from my thing, that will enable me to run on more networks. If that's part of the workload that I'm running, then great, home run. And You know, we come back to this very often because of the insight involved here. When it comes to choice, it's this, right? You're mapping along Wan's triangle, where it's, you know, you have privacy, verifiability, and performance, and it's up to you to select. And what you will have is many different networks that provide these different things. Each network, by the way, inside of each one of these squares, first off, these aren't all the squares. There are probably going to be even more squares. But inside of each square, there are likely to be many networks. Competition is the heart of what will make us successful. We are, you know, the overall system, the protocol, the design is decentralized, so should the marketplace. I like to highlight all of these. These are existing compute over data networks today that we were able to pull together for the compute over data working group. This is even out of date. There's more on top of this. And, you know, our job as stewards of this, and to the extent that we are, and again, no one is leading this, right? It's all a part of the community to bring this together, is to bring all these people together and help everyone agree on these various protocols to implement this kind of execution. And that's the talk. What you will see later today, because I don't want to steal the thunder, is an example of several, you know, networks that already make huge progress towards these goals. And our goal is to like highlight those, but then also many others. So that's it. That's the high level that we've seen, you know, after a year and a half of doing Bacalhau and the Compute Over Data Network. I know that was super high level. Any questions, technical or otherwise?